So welcome to Math 130, Lecture 4. What we're going to be doing today is equations of lines, equations of planes, applications, and then we're going to talk a little bit about some fractals and non-standard dimensions. The reason I want to do a lot of this stuff on fractals is the more meta principle of the class, is teaching you how to look at things. What questions should you ask? Which statistics should you study? You have seen equations of lines for a long time. If I was going to give you a quiz today, I might say, list at least 2 ways of writing the equation of a line from Algebra 1, Algebra 2. You can always forget one of them. What I want us to look at now is a way of revisiting what you've done. And the reason we're going to be doing this is eventually when we're looking at things in multivariable calculus, I do promise the calculus will come, we're going to need equations of lines and equations of planes to describe what's going on. And it turns out that your instinctive sense of how should we talk about what it means for a function to be differentiable is not necessarily the notion that generalizes. And if you look at the equations of lines in multivariable calculus, it may not look like the equation of lines you've seen, but it is once you reinterpret what you're doing. And sometimes when the dimensions are very small, you don't really see the right way to generalize things or the right way you're looking at things. So if I give you a line in one dimension, here's a point, I calculate the rise over the run, and the slope is rise over run. Another way I can write this is m is equal to m over 1. This should not be that exciting. But if I do it like this, I can associate a vector, the vector 1 comma m, and over here I would have the vector run comma rise. And these vectors will be in the same direction. So there really is a vector formulation of the equation of a line in the plane that you've been doing all your life. There's a vector lurking. The vector that's lurking is this rise-run vector. And we've just normalized things. Well, let's just take a unit step in the x direction and then see how much higher we go up. And that's why this is a very natural choice for vector. In higher dimensions, it's not immediately clear what the right step would be. But what's really going on is we have some point, P, and we have some direction, V. And as long as we look at it like that, well, we can generalize this to several variables immediately. It's just going to be P plus some multiple of V. And that's going to be the equation of a line in any dimensions. You have some initial point, you have some direction, and there you go. Is there more than one choice for the initial point? Which point on the line should we take to be our initial point? Any point is fine. Sometimes for the problem you're looking at, there's a point that will be natural. If I'm talking about derivatives of a function at a point, well, that's probably the point I want to choose. But if I want to write down the equation of a line, I just need any point on the line, and I need a direction. And if you want, what's really lurking on is down over here, we have the origin. And so P is this vector from the origin to that point on the line. A more general point, xy is over here, and then I can get that direction v by looking at the difference of the two. And so once I have 2 points, the difference gives me the direction. I could write this down in more detail. I could write it as maybe p sub x, p sub y, plus t vx, vy. And that's another way of writing down the equation. And so you give me a value of t, and I know where I am. Now, if I were to double v, would it geometrically still be the same line? So do v and 2v have the same direction? Yeah. It's basically we're now just running through things twice as fast. When you take t equals 1, we've now gone twice as far as we had before. That's fine. For a lot of things, we often choose the vectors to have unit length because there are some formulas where you have to normalize by the vector's length. The most dangerous thing is that you would forget to normalize. How can you protect yourself from forgetting to normalize? So some formula, yes? Always work with unit vectors. If you always work with unit vectors, it doesn't matter if you forget to divide by the length, because the length is 1. And division by 1 is not going to change anything. But for a lot of problems, 1 is not going to be the most natural thing to look at. So right now, if I wanted to go to 3 dimensions, all I would have to do is add a piece on the bottom, make this a little bit bigger, and then add a VZ over here. And if I want to go to 4 dimensions, similarly, I would just add another row at the bottom. It's not a big deal to do equations of lines. Now, in the lecture that you watched, there were 3 different descriptions of equations of lines. So I asked the earlier section, not one person had done this in their calculus classes. I'm going to assume it'll be a similar number here. I am at least double the age of, I believe, everybody in this room. So this means that there will be some differences in how I was taught and how you are taught. You know, I still remember where I was when Google came out. Okay? Has anybody in this room ever used tables of integrals? Not one person. So when I was in college, we had to have 2 tables of integrals. A short, light table that we could carry on us at all times, and a big, heavy monster that we kept in our room. And one of the hardest parts about using tables of integrals was they were written on paper. You know, my freshman year, you actually had to walk to a building and request an email account. It was not automatic yet. And so you save space, you save cost. And so you don't put down every possible integral. And one of the key skills in using a table of integrals was, how do I convert what I'm given to match the form that's in the book? And what I want to do now is I want to talk to you a little bit, because what we're doing here is we're writing down equations of lines in different ways. And you've seen equations of lines different ways in school. Let me give you the following function and do a little calculus. F of x is sine x cosine x. What's f prime of x? So how do we take the derivative of f of x? What rule? Product rule. So what's the derivative of sine? And the derivative of cosine? Negative sine. And the way you remember that is you have to remember which one gets the minus sine, minus sine. Taking the derivatives, okay? So derivative of sine is cosine, so you get cosine x, so it's cosine squared x minus sine squared x. So that's the derivative of sine x, cosine x. There's another way, however, to take the derivative. Does anybody see another way of getting the derivative of sine x, cosine x? Anybody remember their trig?
Oh.
What trig identity do you want to use? How do you want to rewrite this? This is the same as?
Could you do something weird like 1 over cosecant or something?
No. I mean, you could, and then try to use like the quotient rule.
Yeah.
But I'd have to shoot you for that, because you're using now a cosecant and the quotient rule.
Yeah.
There is, though, a good identity.
It would be like sine x of 1 minus sine of x squared? Or
You would need a square root.
okay.
What if I write it as 1/2 2 sine x cosine x? Does that help you if I write it like this? Does that remind you of which trig identity to use? Anybody remember the trig identity for 2 sine x cosine x? So this is the same as 1/2 sine of 2x. And now if you remember that, then the derivative is 1/2, derivative of sine is cosine of 2x, and then the derivative of 2x is just 2. So this is the same as cosine of 2x. We've actually just proved a trig identity. We've proved cosine 2x is cosine squared x minus sine squared x. Do those two functions look the same or do they look different? Yeah, they look different to me. Okay, cosine 2x looks very different than cosine squared x minus sine squared x. But they're the same function. And this is the point of a lot of what we're doing, is we're looking at different ways of doing the same algebra. And depending on how you do it, it might be better or worse for the given problem that you're looking at. And a lot of the skill, it becomes an art, which is the way that's going to help the most. This is why we have multiple ways of doing things. So depending on what information I give you, one way might be the more natural way of writing it down. Which function would you rather plot, cosine 2x or cosine squared x minus sine squared x? Yeah, I'd much rather plot this. I'd much rather avoid the product rule. This has a lot going for it. It unfortunately requires you to remember trigonometry. So, trade-offs. To just really drive home the point, why do we work base 10? Yes.
Number of fingers.
Yeah, number of fingers we have. Could we work in other bases? Absolutely. And we'll see later today a nice application of base 3. Anybody know what base the Babylonians used? And it's still with us today. If you think about times in the day or angles in a circle, you might have an idea of what base the Babylonians used. So they were base 60. And no, we didn't start off with 60 fingers, 30 on each hand, and over time we evolved to the point of just having the 5 we have now. The Babylonians loved base 60 because 60 is divisible evenly by so many numbers. 1, okay, well that's not a big deal, but 2, 3, 4, 5, 6, okay, not 7, not 8, not 9, but 10, 12, 15. It splits very nicely. Now, I will assume nobody here knows their 13s tables. Who here knows their 12s tables? 11s tables? 10s tables? At 10s tables, everybody's hand should be up. If you do not know your 10s tables, this means you can't multiply things like 7 times 8 and 2 times 9. Knowing your 10s table is a prerequisite for how we do our positional arithmetic. How many multiplications do you need to be able to do if you want to multiply one-digit number by one-digit number? In base 10, how many multiplications do we need to know? So what's your first guess? How many multiplications if we want to be able to do one-digit number times one-digit number? How many things do we have to memorize?
Including repeats.
100 including repeats. Excellent. And so I love the fact that you said including repeats, because 3 times 4 is really the same as 4 times 3. So we can almost cut it in half. But then, oh crap, 4 times 4 is the same as 4 times 4. So it turns out there's 55, but it's essentially half of 100. Now for the Babylonians, base 60, how many multiplications do they have to know? So if you were a young Babylonian learning math, how many multiplications would you need to know? So this should be roughly 1/2 of 60 times 60, or about 1,800. So I want you to learn for one. No, I'm not going to assign that as a homework assignment. You would be correct to go to the dean's office and say, I don't know what's wrong with my professor, but he wants us to memorize. Especially in the 21st century, this is absurd. Now think back to Babylonian times. Do you want to memorize on the order of 2,000 items? So you would just have a lookup table. Unfortunately, they don't have the great paper we have now. What would they have it on?
Tablet.
Tablets. And so you either have to lug them or have somebody lug them for you. And that is a lot of stuff to have written down. So the way the Babylonians multiplied numbers, they want to multiply x and y. At first this looks like the most absurd thing you've ever seen, but it's actually one of the greatest ideas in mathematics. X plus y squared minus x minus y squared. The chalk was willing to give its life for this, divided by 4. So we should appreciate its sacrifice. Now, when you look at this, so rather than doing one multiplication, I'm going to do 2 different multiplications, a subtraction and a division. And I'm going to be happy? Yes. The reason I'm going to be happy is, what kind of multiplication am I doing? Am I doing a general multiplication of 2 general numbers? I'm just squaring things. I only need a table of squares. So if x and y go from 0 to 60, this goes from 0 to 120. So I only need to learn on the order of 120 things. And now I do a subtraction, which is easy, and dividing by 4 isn't bad. This is a general principle. I would much rather do a lot of very simple tasks than one very hard task. Break a big, complicated problem up into a lot of smaller steps, do them. So this is the reason I really wanted to talk about stuff like this. Depending on how you look at the problem, you can make the algebra harder or easier. And depending on how you do it, you're going to be able to look at it and see what's going on. So we're going to have lots of different ways of looking at functions. Right. So we talked a little bit about equations of lines. We're going to move up now to equations of planes. And the main reason we're going to be doing this is to generalize one of the most useful ideas in one-variable calculus. And the idea in one-variable calculus is, if I give you any complicated function, if it's differentiable, then what does that function look like locally? It's continuous, but what does it look like locally? What shape? So this is one of the key. If I give you some strange function like this, if I look at it in a very small neighborhood, doesn't matter what neighborhood I look at, and I zoom in, it's going to look like a straight line. So this is the fundamental idea of differentiable calculus, that locally every differentiable function is a straight line. Imagine for every minute you study, you'll get 1 point higher on the first exam. Okay? How many minutes should you study? 100 minutes. Really? What happened if you studied 110 minutes? I mean, you're getting a point a minute. Why stop at 100%? Why stop at perfection? Why not go beyond? This way you can screw up the next exam. You can screw up the final. You can get so many points on that first exam, you're done. Okay. The absurdity, of course, is that, yes, you may be able to get a point per minute, but that can't continue indefinitely. You're not going to break 100%. So the idea of this approximation, it can work locally, but globally it will probably break down unless your function happens to be a straight line. If your function is a straight line, it's going to be a perfect fit. Later in the semester, we will talk about Newton's method. It is what converted me from physics to mathematics. So let's say I give you f of x is x squared minus 3, and I want to find where this is 0. So can someone tell me where x squared minus 3 is 0? And? Okay. And what is root 3? You've just given me a name of something. Well, what is root 3?
Value for x.
Okay, and what is that number equal to? Okay, and what is that equal to? I want a number. Can anybody tell me approximately what root 3 is?
What, 1.2?
1.2 is too low, because 1.2 squared is 1.44. So it's a, yes?
It's between 1.1 and 2.
It's between 1.1 and 2. So I saw somebody, I think, trying to take out their calculator, which is great. I strongly urge you to do something like that. It's about 1.732. That's the start of it. but it's an infinite decimal. It never repeats. Well, what is that value? Well, the idea, and we will do this in great detail, is let's guess 2 as my initial guess of square root of 3. Do you all agree that this is not a good guess? What I do is I will go to my function, and I will calculate the tangent line to the function at 2. And I will replace my function with the tangent line, and I will see where that intersects. And that intersects at the point 7/4, which is 1.75, which is pretty close to the square root of 3. And then I will lather, rinse, repeat. I will then draw the tangent line here, and I will see where that intersects. And it turns out if I do that, I think it's 97/56. It's incredible how quickly this converges to the square root of 3. It's amazing how well this works. And the idea is we are replacing a complicated function with a linear one, and then we're kind of piecing things together. And this is one of the major themes of calculus. It turns out that this leads to fractals, which we will be talking about at the end of today's lecture. But it gives you some sense of the value of differentiation in one-variable calculus. And it gives us the notion of what we want to generalize and why. You should be a little bit upset this is a multivariable calculus class and we've done almost no calculus. The reason is we have to build up the language. And the question is, what is the right way to generalize the derivative in one variable? So we can calculate the partials df dx and df dy. This was the better section. It took you guys only 30 seconds to do it. But maybe that was because I was prepared. It took 32 seconds in section 1 to do this, right? To calculate the partial of f with respect to x, consider all other variables as constants, and then just take the derivative normally. Calculating these is not hard. It's less than a minute to learn. But just because these partial derivatives exist does not mean the function is differentiable. And the correct notion of what does it mean for a function to be differentiable in several variables, you have to be able to approach through any possible limit construction. In the line, how many ways are there to approach a point? There's 2 ways. I can come from below, I can come from above, from the left or from the right. That's it. It's boring. In 3 dimensions and higher, in 2 dimensions and higher, I could take a strange path like this, and I have to be able to handle an approach like that. My son loves planes, and I'm just trying to imagine some plane coming to a runway, flying along this route to land. It's a valid route. We have to show that the limit exists no matter how you approach. And it turns out that the real way to view a function as differentiable in one dimension is that the tangent line is a terrific approximation to the function. That's the notion that's going to generalize. And a line will generalize to a plane when we look at a function of 2 variables. And then a hyperplane when we look at a function of 3 variables. This is why we're going to be spending so much time learning how to take a bunch of vectors and calculate equations of planes, because we want to be able to do calculus. And to do calculus, our function will be differentiable if the plane does a great job. All right, so now we need equations of planes. And this is going to be very similar to the equations of lines. It's going to come down to what information do I give you. Depending on how I give you information, you will write down the equation of the plane in many different ways. One of the simplest is, here's my origin here. I have some point P over here. And I give you 2 directions, V and W. And if I give you 2 directions like this, this is going to be the easiest way to write things down. I would have, it would be my point P plus TV plus SW. So here's my point, here's my 2 directions. If V and W are in the same direction, what kind of object is this? So V and W are in the same direction. What kind of object would you have? So let's say W equals 2V. We get P plus T plus 2S times V. What kind of object is that? it still looks like a plane. I have two free variables. But I claim this is not a plane. What kind of shape is this? It's a line. I could just call this as some new variable u. This is really just p plus uv. And there's infinitely many ways to get the same value of u. I could take t equals 2 and s equals 1, and that would give me a value of 4. I could take t equals 3 and s equals 1/2. It's just a line. I don't want to consider a line as a degenerate plane. I really want a plane to be 2 dimensions. I don't want v and w to be in the same direction. So we will always assume that we have 2 different directions when we're trying to write down the equation of the plane. If I give you p, v, and w, then the problem isn't too bad. But I might not give you p, v, and w. What I might do is maybe I give you 3 points. So here's p, here's q, and here's r. So they're all coming from the origin over here. There's the vector to p, there's the vector to q, there's the vector to r. And I want to calculate the equation of the plane. I can use either p, q, or r as my base point. Which one do you think I should use? P. It occurs first alphabetically. You could do it, of course, with r and q. I can look at q minus p. And so if I let v be q minus p, that's my first direction. And then similarly over here, I will have w be r minus p. And so if I give you 3 points, I can calculate the 2 directions v and w, and now I can write down my equation of my plane as before. If we were in more dimensions, more generally it would be p plus t1 v1 plus t n minus 1 v n minus 1. When we're in 3 space, we have 2 free variables. If we're in n-dimensional space, we would have n minus 1 free variables. We'll talk about this again in another moment. Any questions so far on what we're doing? There's another way to do it, the normal direction. And this is where we luck out in 3-dimensional space. If you have a plane, another way of viewing the plane is it's all points such that the vector formed from that point to your base point, your starting point, is perpendicular to a normal direction. So for this piece of paper over here, I could make the number 3 be my base point. I choose some vector that's perpendicular coming out of the plane like this. And then you give me any other plane in here, and if I draw the vector from there to 3, that's going to form a right angle with this vector coming out. And the reason this works is there's 3 dimensions in the plane. I'm sorry, there's 3 dimensions in 3 space, 2 dimensions for the plane, that leaves 1 remaining direction coming out. So in this case, I would have, here's my vector p, here's my normal direction, and then I want all vectors here, x, y, z, such that their dot product with the normal direction is 0. And this is where we use the dot product. The dot product is a very nice way of telling when 2 vectors are perpendicular. 2 vectors are perpendicular if the dot product is 0. So if I want to look at what's going on, well, if I want to calculate this vector, it would be x, y, z minus p. And so the equation I get is I would get n dotted with x, y, z minus p. And what should that equal? 0 the number or 0 the vector?
0 the number.
0 the number. Why is it 0 the number?
Dot product.
Dot product is a scalar. If it was the cross product, it would be a vector. So if I say maybe the normal vector is a, b, c, you would get ax plus by plus cz equals n dot p on the other side. And this is another way to write down the equation of a plane. And this is the more standard way you've often seen. If c is not equal to 0, we can actually solve for z. And we get c is equal to n dot p minus ax minus by over c. What I like about this view is if I give you x and y, then z is uniquely determined. And you can see now that this really is a two-dimensional object. You always want to get a sense of what is the dimension. Are we talking about a vector? Are we talking about a scalar? How many degrees of freedom do we have? A plane should have 2 degrees of freedom. And once I fix x and y, then z is uniquely determined. So the question is, how can we come across with n? How can we find that direction? Well, as always, it depends what you're given. If I tell you, I want a plane through this point, where this is the normal direction, well, then it's not going to be too hard to find the normal direction because I'm giving it to you. If instead I give you 2 vectors v and w, how could you find the normal direction if you know v and w? You could take the cross product. So cross product. So the first thing is, the first question people had asked me to discuss was, why are we defining lines as the difference between 2 vectors? When you look at this picture, if I have my arbitrary point x, y, z over here, let's just blow up this triangle. Here's 0, here's p, and here is the x, y, z. And then going from 0 to p and then p to here is the same as just going directly from 0 to here. So this vector plus this vector equals this long one over here, or this long one over here minus this one over here is that direction over here. And this is why we like to calculate things like this. And if I look at the difference of those 2 vectors, it's going to give me a vector pointing in the direction from p to x, y, z. The cross product is a great way to calculate something perpendicular to 2 given directions in 3 space. Given that I am doing this on the board, I will use simple numbers. Let's take v to be 1, 0, 2, and let's take w to be 0, 1, negative 1. There's about an 80% chance that these are the same vectors I did in section 1. I did not care enough to, because it doesn't really matter. You could, if you want, remember the formula for the cross product. Or you could just write things down and copy the first 2 columns. I would much prefer just copying the first 2 columns. 1, 0, 2, 0, 1, negative 1. And then we'll write again as I hat 1, 0, j hat 0, negative 1. So we have the 3 going down with a plus sign, and the 3 going up with a minus sign. So I hat times 0 times negative 1 is just 0. J hat times 2 times 0 is just 0. K hat times 1 times negative 1 is going to be minus k hat. This is b cross w. Now we do the minus ones. It's going to be 0 times k, that's 0. 1 times 2 times I hat, so that's minus 2 I hat. And then the last one is going to be minus 1 times 1 times j hat. So it's going to be plus j hat. So we get minus 2, 1, minus 1. Okay. Did we make a mistake? Oh, no, this one should be a plus 1. Because it's minus 1 times 1. It's minus 1 j hat, but we have to put in the minus sign because we're doing the minus 1 over here. So these 3 are with a minus sign. It is inexcusable in this class to calculate a cross product incorrectly. Yeah, there's a couple things that make me really upset. What's one thing that makes me really upset? I got this in section 1. You could say either rooting for the New York Yankees or forgetting to say area when you talk about the fundamental theorem of calculus. These are things that will set me off. It is inexcusable to calculate over here the cross product to try to find a vector that's perpendicular to v and w and get it wrong. It's okay not to know how to do it, but it's not okay to do it wrong. What can you do with your answer here? You believe that this is the answer. You believe that this vector is perpendicular to v and w. What can you do? Check. So you can check and see, well, does it work? So v cross w, we claim, is -2, 1, 1. -2, 0, +2, good. That dot product is 0. 0, 1, -1, good. That dot product is 0. So we can at least check the work and see if the answer is reasonable. It's not a proof that we're correct, but you should always check whatever math you can. Now, if I asked you to just find a vector that's perpendicular to 1, 0, 2, you can often do this by inspection. Find u such that u dot v is 0. And I claim if I take u to be -2, 0, 1, that works. And if you just do the dot product, you will see, yes, I get -2, 0, +2, that works. It's not hard to just find one vector that's perpendicular to another. Unfortunately, the odds that it's going to be perpendicular to my second one is very small. And if I do the dot product, I would get 0, 0, -1. So it doesn't work. I'm going to show you an advanced way now. It is absolutely fine never to use it. But one of the things I could do is say, well, you know, I actually have some freedom here. I can put anything I want in the middle, and the dot product is still going to be 0. So if I look at all vectors of the form -2, y1, anything of that form will be perpendicular to 1, 0, 2. And then I choose y so that hopefully I can solve the second one. So this is another way. If you have more than one way of doing a problem, you have a chance to check your answer. One of the things you have to be careful about, and this goes back to the table of integrals, is your answers may be in a different form than the book. And maybe your vector has twice the length. Well, that's fine, because for the normal, I only care about the direction. I don't care about the magnitude. Okay. Any questions on what we've done on equations of lines, equations of planes, how to calculate them? Depending on what information you have, you will calculate things in different ways. Okay, so for the last couple of minutes today, I want to talk a little bit about fractals. Partly because it's really cool math. Later in the semester, when we do Newton's method, we will do more with fractals. It is a requirement when you have a video like this that there's typically cheesy music playing in the background. If you want, I will definitely have the music playing. I apologize, the video I made does not have the cheesy music. But if you think about it, we've been implicitly making certain assumptions or limiting ourselves to certain discussions. We've been talking about equations of lines. How many dimensions? A line has how many dimensions? Not 2. 1. So if you think of a line is a point plus a multiple of a given vector. Once you tell me the multiple of that vector, I know exactly where I am on the line. There's only one piece that's free. How about a plane? How many free parameters do we have for a plane? So line was P plus TV. We had one thing that was free. A plane is P plus TV plus SW. How many free parameters do I have for a plane? 2. How about a hyperplane in 4-dimensional space? That would be 3. These are nice integer dimensions. Is everything in life an integer dimension? And so we need to come up with a way to talk about dimension that will reduce to the notion that you already have in your mind, that I will not ask you to mathematically formulate right now, but will also work in other settings. And again, the main reason I want to do this is what you study as you go further, you often have freedom. And you have to find what is the right quantity to look at. I have to be careful because this is being recorded. Later today, I will be talking with somebody about some consulting work I will be doing soon with some Williams students. And a big part of this is, well, what is the quantity you're going to be studying, and why is this the right one to study? Let's say you have some object, and you expand each direction by a factor of r, and you get c copies of what you start with. Then the dimension d satisfies r to the d equals c. This is the big equation. Okay. Whenever you have an equation like this, you want to test it. Let's look at a line segment. If I triple the line segment, how many copies of it do we have? So if we triple the line segment, so r would be 3, how many copies of that initial line segment do we have? 3. So then when we solve r to the d equals c, we get d equals 1. Good, a line segment has dimension 1. If that was not the case, we'd be in trouble. Let's look at a square, and let's triple everything. So again, r equals 3, but now how many copies do we have? 9. And when you try to solve 3 to the d equals 9, what a shock. D equals 2. I'm not going to draw a cube. If I were to draw a cube, what do you think you would get for the dimension? What would you get for the dimension of the cube?
81.
Nope, I'm asking for the dimension. 3, right? You should get a cube as 3 dimensions. It turns out that there are some very nice sets which have dimensions that are not integers. And the first is the Cantor set. And then after this, we'll get quickly to the Pascal's triangle. So for the Cantor set, you start off with the segment 0, 1. And then you throw away the middle third each time. Throw away middle third. So the next iteration, we go from 0 to 1/3, and then we go from 1/3, I'm sorry, from 2/3 to 1. Then on the next iteration, we go from 0 to 1/9, 2/9 to 1/3, 2/3 to 7/9, and then 8/9 to 1. Each time we throw away 1/3, how much do we keep? 2/3. So initially we have 1, then we have 2/3 for our length, then we have 4/9, then 8/27. So in the limit, what is the length in the limit? The length will go to 0. So this is something that should have, in some sense, dimension less than 1. But there's still infinitely many points. Now we talked a little bit about why we like to use base 10. My daughter's 5th grade teacher has a nice sense of humor. I've known her for years. I had my daughter teach her how to count in binary. So you want to count in binary. 1, that would be 10. It's 1, 2. That would be 11. I'll let you continue counting. You can count in base 2. You can count in base 3. If I take any number here, if I write my numbers in base 3, then every number between 0 and 1/3 has 0 as its first base 3 decimal digit. Well, decimal's bad because decimal's base 3. everything from 1/3 to 2/3 has its first digit as 1. Everything from 2/3 to 1 has its first digit of 2. Over here, we throw away all things that have a second digit of 1. And then we would throw all things that have a third digit of 1. So what you're left with is a number whose base 3 expansion only has 0s and 2s. So if I write my number, I can write it as the following: an over 3 to the n, where each an is either 0 or 1 or 2. But that means I could look at instead this new number, an over 2 to the n, because an over 2 is always going to be an integer. What this is telling us is I can put this at basically in a one-to-one correspondence with the entire segment 0, 1. It's the same number of points, just rearranged. The whole point of this is that you have to be careful with infinities. And so there's as many points in this Cantor set as you started with, but somehow it has 0 length. But it doesn't have 0 dimension. So I want to figure out how much should I rescale things by to get a nice number of copies. So do you want to rescale things by a factor of 2 or a factor of 3? What do you think?
Factor of 3.
Factor of 3, we've got a 1/3 over here. If I triple everything, then this segment from 0 to 1/3, well, that just goes up 1 level. So this part, what's coming down from this chain over here, if I expand by a factor of 3, it just becomes another copy of my original set. And this becomes another copy of my original set. So if I take r equals 3, then I get 2 copies. So 3 to the d equals 2. So the dimension is the log of 2 base 3, which is strictly less than 1. So the Cantor set has a non-integer dimension. So for Pascal's triangle, just as we're running out of time, what we do there is we throw away the middle triangle every time. And so we start off, we first throw away this middle triangle. Then on the next stage, we throw away these triangles. What fraction do we keep each time? We keep, I think I heard it. We keep 3/4. So we initially have the whole thing, then we have 3/4, then 9/16, then 27/64. And so in the limit, what fraction do we keep? We keep 0. So the area goes to 0. The perimeter, however, is very different. We always have the outside, and in fact, as we keep iterating, the perimeter is growing. The perimeter goes to infinity. The dimension of this is somewhere between 1 and 2. So if this is 0, this is 1/2, and this is 1, do you want to double everything or do you want to triple everything? Double. And then this triangle over here, when you double, expands to the whole thing. This would expand to a whole thing, and this would expand to a whole thing. How many copies do we get? So if I equals 2, how many copies do we get? We get 3. And so now when we solve 2 to the d equals 3, that implies d is the log base 2 of 3, which is less than the log base 2 of 4, which is 2. So the dimension is really above 1 and less than 2. So we will see a lot more of fractals when we get to Newton's method. You often sometimes hear about this as extreme sensitivity to initial conditions. But the real reason I wanted to do this is to just talk to you about the importance of finding what is the right object to study. You can study things that have non-integer dimensions, but you want it to collapse down to the nice things that you know. Similar to, we want to take the stuff we know about lines, and we want to expand it up to higher dimensions. So again, I really want you to get a sense of why we're choosing to study what we're studying. All right, so